Last time, we saw that Simpson's rule can be derived by starting with the assumption that each panel is bounded by a parabolic arc. Before that, we saw that the trapezoid rule can be derived by connecting line segments between function values. The next extension would be interpolating a cubic polynomial through the data points, integrating that, and seeing what pops out. If you missed the last lesson, I recommend watching it before moving on. A lot of the steps are going to look very similar, but the explanation may be abbreviated here since we already discussed matters in more detail. From this graphic, we can see that a cubic polynomial fits closer to the blue curve than either a parabola or a straight line segment would. Notice that 4 data points are needed to interpolate a third-order polynomial. Our data points are evenly spaced once again. This time, we are going to set x0 equal to 0. In equation form, this is what the orange lines on the previous page represent. So we can represent x1 as h, x2 as 2h, and x3 as 3h. y0 is a function of x0. Substitute 0 into the expression. y1 is a function of x1. Substitute h into the expression. Similarly, y2 is a function of x2. Substitute 2h into the expression. Lastly, y3 is a function of x3. Substitute 3h into the expression. Here is a summary of the results from the past 4 slides. In each case, y is represented in terms of mesh size h and the unknown coefficients a, b, c, and d. As always, we can represent a system of linear equations by a matrix. That simplifies the bookkeeping quite a bit. Since this is only a 4x4 matrix, go ahead and take the inverse to solve for our unknown coefficients. In equation form, the answer is shown here. Coefficients a, b, c, and d are expressed in terms of y0, y1, y2, and y3. Remember that we usually get these y values directly from a data table, so they are known quantities. The area beneath a curve is calculated by taking the integral. So now we integrate the cubic polynomial we started with. Notice the lower limit 0 corresponds to x0, and the upper limit 3h corresponds to x3. So it is that we are integrating from x0 to x3, as seen by the pink panel at the beginning of the lesson. The details of substitution require a bit of patience. I have included them here for those of you who wish to follow along at your own pace. However, I will not belabor this step of the process. Just know from a high-level overview that we are substituting the expressions for coefficients a, b, c, and d into the definite integral. In the 4th line, I have simply distributed the term out front to each term inside the parentheses. Then I found a common denominator of 24 for each fraction. By the 6th line, I have collected the coefficients for y0, y1, y2, and y3 separately. Next, I add those fractions together and simplify to lowest terms. In the very last line, I have factored out 3/8 in front. That was for one panel. As with any composite rule, we can add multiple panels together. Once more, y0 and yn have a coefficient of 1. Everything else is multiplied by 3, except for those terms in blue, which are multiplied by 2. Are you seeing the pattern by now? Remember that Simpson's rule required the nth data point to be even, divisible by 2. This method requires n to be divisible by 3. That's why we see y3, y6, y9, and y12 as the last term in each line. This pattern can be generalized and represented in sigma notation, as seen here. Unfortunately, this method is also called Simpson's rule and can be confused with the other Simpson's rule. For that reason, we refer to this method as Simpson's 3/8 rule to distinguish it from the other one. So line segments between y values yield the trapezoid rule. A parabolic arc through 3 y values yields Simpson's rule. And a cubic arc through 4 data points yields Simpson's 3/8 rule. Can we keep going with a 4th or even 5th order polynomial? Yes. These get into what are called Newton-Cotes formulas. However, remember what we learned about Runge's phenomenon when studying interpolation? High-order polynomials pass exactly through the provided data points, but they tend to oscillate wildly between those values, giving anything but a smooth fit. Consequentially, the resulting integral of such a polynomial would not give a very good estimate for the area beneath the curve. For that reason, Simpson's rule is usually a good stopping point if you want to numerically integrate a set of evenly spaced data. Back to the sigma notation on this screen. So what about that h to the 4th at the end? How do we know this is 4th order? Well, you'd have to derive this differently to know that for sure. Nevertheless, in the next lesson, we will run some numbers through Simpson's 3/8 rule, and the results will show 4th order convergence. Stay tuned for that.